Welcome to Algebra 2. You have a poll down there in the corner. Hit the little 9-dot square thing, and there'll be a poll. So I want everyone to get that answered this morning. And I'm going to put our estimation up here on the screen. Let's get our guesses. Now, this is a little different than last week because you're like, oh, I know the answer. This time, we're asking about like a staple gun. A staple gun. Now, last week we looked at just a regular strip of staples down here, and the regular strip of staples had 210 staples. They're very skinny. They're just putting paper together, right? So that's what fits in a stapler. But a staple gun, as you can see, those are much fatter. These are heavy-duty things. I mean, you use this on lots of things bigger than paper to hold things. So I mean, you can go into some woods. If it's a soft wood, you can do a staple gun into some serious wood here. So these are much heavier duty than these little skinny ones we put in our stapler. So there's 210 we know in the strip on the right, but I'm asking you how many staples are in the one on the left. That they're taller, they're thicker. So put that in the chat. What kind of guess do you have? How many are in a strip of staples for a staple gun? Some of you may have used a staple gun, but I would imagine most of you probably haven't at this point. That's some heavy duty ones. I'm saying 100, 150, 90. All right. 100, 125, 100. Yeah, definitely less than the 210, right? We know 210. Those are really, really skinny. These we can see each individual staple. They're so wide that there's definitely not 210 in there. 100, 115. All right, seeing some good guesses here. Could be some really, really close guesses. All right, let's take a look. Let's see who's right. Anybody get it exactly? 78. All right, so there's not very many at all compared to the 210. There's just a little over a third. But you can see how big those are. They're pretty wide, and all the 78. So it's not bad. You guys did pretty good on that. Let's look at the next right here. So how many come box? If 78 come in a strip, he's blacked out how many strips there are in there, but they would stack those up again 2 by 2. Match color. Interesting. Okay. So blue and blue. So these will fit in this staple gun right here because it's blue. So these are 1/2 inch tall or 12 millimeter tall. We know there's 78 in a strip. So how many is going to be in a box? It's like, man, you took away how many strips there are on the side there. 780, 1200. Of course, when it was like the other staples, it had like 210 in a strip, and it said there was 5,000. When that didn't really work mathematically, but there's probably 5,040. But all right, get some more guesses out there, folks. If you haven't taken that poll, get the poll taken there. Give it a guess. You don't get a grade on this. 800, 1,000, 1,100. All right. A lot of people thinking there's 10 strips in there, so 780 is a popular answer. 600's up there. 677. The Marion's just going to throw something different out there. Let's get a crazy number out there. Let's see. All right, we got a lot of guesses out there. Let's go back and see what there actually is. 1,250 about. It says there on the box about 1,250. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's about 16 strips in one of these. Let's see what it would be exactly if there's 78 on every one and there's 16. 1,248. So it's saying about 1,250. So 1,248. You guys were not bad at all on these guesses. You get right in there. I saw it's 1,200 up there as a guess. That was pretty close right there. All right, let's go back and look at two more. Let's do two more. So how about a little stapler then? Keeping on the staple theme. They make these little bitty ones. Just fit right in your hand. So this big one, we said 210. So how many staples are going to be in this little bitty strip that goes in this handheld stapler? Then you know we're going to have a box next, right? I say guess a 25, 20, 50, 20, 42, 30, 35, 15. All right, we're getting a lot of good guesses here. I haven't looked at this yet, so I don't even know the answer, but I would be right there with you guys. I would think 30 is what I would guess. Just looking at it. I don't know. Let's see how we did. 67, 40, 50. Oh, there's more than I thought in there. All right. Did anyone say 50? No, we had, yeah, Truman said 50. Nailed it. We had some good guesses there. So these are looks 1, 2, 3, 4. Yeah, the others has 210. These may be just a little bit wider than those, but 50 staples. So now we know the next one, right? They're going to have a box of those, right? Yep, there they are. There's 50 in a strip. Oh, it looks like the strips fit this way, and looks like it's probably tall enough to stack them, and they probably put them inside each other. I bet there's a lot of strips in there. But it would go, yeah. So Braden's going to jump out there at 800. That's probably a pretty good guess there. 1,000. See, there's a whole bunch more of them long strips, but this is going to be pretty good. 250, 850, 500, 500. How many's going to be in this little box? 600, 500. I see 850. Let's see. Let's see. 1,000. Olivia said 1,000. Nailed it exactly there. So there's 1,000 staples in there, 50. So there should be what, 20 of these in there. So 5, and then they turn one upside down, 10, and then they stack them double high. All right, very good. Very good. All right, we're going to move on and look at, I want to look at my poll. Let's see how we did on polls. Where's the poll? There it is. All right, I'm going to end the poll. See how many people have done it. 14 of you have done it. That's good. We got 14 in there. In the poll. And what is the answers? I'm going to see if I can show everyone the results. We had 10 votes for substitution and elimination. And we had 1 vote for all of the others. 1 for Pythagorean theorem and substitution. Pythagorean theorem has to do with like a triangle, guys. A squared plus b squared equals c squared. We did not do that. Factoring and expanding, subtracting and canceling, integrating and differentiating. That's more in the calculus, guys. We didn't do any differentiating. So, all right. I just wanted to put that out there and see how everyone was doing, remembering last week and what we did. But we looked at solving systems of equation algebraically. And yes, it was by substitution and elimination. This week, we're going to look at solving systems of equations graphically. And then I want to review this substitution elimination, because we need to not just totally put that behind us. That's where we do a lot of times. Okay. Can you read a subway map? They've got to blurred that one, but what if you needed to get from one station to another but have to change lines? How do you know where the red line meets the green line, where it's possible to get from the yellow line to the orange? Reading a subway map is sort of like looking at the graph of a system. Lines sometimes intersect, sometimes they don't cross. Some lines may run along the same path. And as you work through the process of graphing, imagine the lines of subway tracks to make your commute a little easier. Now, we don't have a lot of experience reading subway maps here because we don't have any subways in our area. Some people this would make a lot of sense to. But let's let's look at a subway map just to see more of what they're talking about. So we can relate a little bit to what they're saying. Okay, this is a subway map for the New York City subway. So if you're trying to get from over here somewhere to over here somewhere, from this corner to this side over here, you'd have to figure out which subways can I take to get there. What I go, maybe I want to go right up here at the top green, and I'm down here in this red and green corner. I got to figure out, do I have to change subways? If I'm on the blue subway and I want to go up here to the very top middle where it's only red and green, I've got to get off the blue subway and get onto the red subway at some point. So I got to figure out which stop I need to get off and which stop I need to get on to switch subways. And boy, that's a lot going on there. All these subway stops. So that's what that's talking about. I'll do a quick little aside story because kind of like relating this. I keep this picture in the back. I don't know how many of y'all seen this back there, but that's my wife. That's my wife right there in Paris. This was 18 years ago. And we were going to the Eiffel Tower. We were going to eat dinner there. My wife didn't know we was eating dinner there. I surprised her. She didn't know we was going to the Eiffel Tower. But we left our hotel and we got on the subway in Paris. And my wife said, "You're going to get us lost in the subway." I said, "No, I talked to the concierge at the hotel. He told me where to go." Well, he told me just the name of the stop I needed to get off. But I had to get down the subway, and I'm looking at all these names, and everything's in French. I don't read French. My wife doesn't read French. But I just knew the word I was looking for that named the subway stop. And so I'm looking to see which direction I go. He gave me the directions. But that was interesting. We made it there. We didn't get lost, but yeah, riding the subway map when you can't read anything is even a little trickier, I gotta say. So at least if you could read the language that the subway's in, you got a better shot. But that was interesting. All right, we're going to learn how to answer the following questions. How can graphing methods be used to solve a system of linear equations, and how can multiple representations of a system be graphed? All right, let's go over here and look at page 2. All right, we got a video right off the bat. So let me share this in a way that you can hear it, because if I don't share it properly, you can't hear what it's saying.
Hello, today we're going to look at graphing system of linear equations. So I have 3 systems here that we're going to go ahead and graph. The first one here, you'll notice that the first thing we need to do is put it in slope-intercept form. So I'm going to take my x minus y is equal to 3, and I'm going to put it in slope-intercept form by subtracting the x from both sides. This gives me a negative y is equal to a negative x plus 3. Now I'm going to go ahead and divide everything by this negative 1 so that I get a y is equal to x minus 3. I'm going to graph this. My y-intercept in this case is going to be a negative 3. And the slope is 1 over 1, which means I'm going to go up 1 and over 1. Now I'm going to do the same thing with the second equation. I have 4x plus y is equal to 2. I'm going to go ahead and subtract the 4x from both sides to get y is equal to negative 4x plus 2. I'm going to graph it on the same coordinate plane. So I'm going to go to 2, and then I'm going to go down 4, 2, 3, 4. And over 1. And look at that. We have a perfect point of intersection. Let's go ahead.
Okay, I'm going to pause that there. She's graphing them by hand, and to graph by hand, we need it in a mx plus b form, right? Y equals mx plus b. So that's what she's doing, is she's rearranging these 2 equations up here to where it's y equals x minus 3 instead of x minus y equals 3. And then instead of 4x plus y equals 2, she's doing y equals negative 4x plus 2. So they can be graphed by hand. Now, here's the nice thing. In this class, we use Desmos to graph. You can graph by hand. If you like graphing by hand, please, by all means, do that. But let's switch over here and look at Desmos. We're going to graph the exact same things that she just did. And I'll show you how in Desmos we can do that a little easier. Because the first equation she had was x minus y equals 3. We can just type that in as it is. X minus y equals 3, and there's the exact same graph that she created. Now, she converted it to be, let's see what you do. Y equals x minus 3. y equals x minus 3. Look, that's the same line. See, it just turned blue. The blue line is the same as the red line. So we do not have to put it in a y equals format to graph in Desmos. We can just type it in as it exists. Let's see, what was the next one? 4x plus y equals 2. 4x plus y equals 2. And there's that same line of intersection that she found. That is the solution to this systems of equation. The point 1, negative 2. When x is 1 and y equals negative 2, both of these equations are true. X minus y would equal 3. 4x plus y would equal 2. So we don't have to watch all of this video because she's going to do the same thing with these. But you can just type them in exactly like they are to get the solution. So you'll be asked to find the solution to a system of equations. A system of equations, 2 more equations with the same variables. Okay, that's 100%. Before you learn to do that, review what it means to have a solution. All right, let's talk about solutions because we looked at a few different cases last week. And we said, let me emphasize this. We said we could have a solution to a system of linear equations. They're lines. We can have a solution like we did on the graph we just now looked at. 1, negative 2 was a solution, right? Because that's where the two graphs cross each other. That point exists on both lines. The same point exists 1, negative 2. So that's one solution. We could have infinite solutions. Remember, we looked at that last week. That where if they're the same line, every point that's on this line is also on the other line because they're the same line. So there's an infinite number of solutions. It's all the points that's on the line because they're the exact same line. It's not any number because there's lots of points that aren't on the line. All these points over here are not on the line, but there's an infinite number of points that are on the line and they're the same line. So that's infinite solutions. There was also the possibility of no solutions. Remember when we graphed it and they were parallel lines? They were parallel and they never touched. So there's not any point that was on both lines. So in that case, there's no solution. So we could have one solution, we could have an infinite number of solutions, or we could have no solution. And we saw that when we did it algebraically last week, because sometimes we'd solve it and we'd get x equals 1, and we'd put it back in the equation and get y equals 4, and the solution was 1, 4. But sometimes we did an equation that said like 0 equals 0. That was the infinite solutions because 0 always equals 0. Or we got like 0 equals 9. Which is not true, which means there's no solution. So we can see it graphically and algebraically when we're working those. All right. Let's get back to what it is. What does it mean to have a solution to something like 2x minus 4 equals 10? Which of the values below is the solution to the equation 2x minus 4 equals 10? Well, let's take a look at that. All right. I'm going to put that on our paper. Because there's only one variable. So we can add 4 to x equals 14, divide by 2. In this case, if x equals 7, then 2x minus 4 equals 10, because 2 times 7 minus 4 equals 10, because this is 14 minus 4. So that is true, 10 equals 10. So if x equals 7, this is a true statement. 10 equals 10. So 7 is our solution. Submit. Correct. It's the one and only solutions. There's not another number we can put in. 2 variables. What does it mean to have a solution to something like 2x minus 3y equals 6? Select the correct answer, hit submit. So if x equals 0, that we have to test. Let me write this equation. 2x minus 3y equals 6. So here's our possible answers. 0, negative 2. I'm just writing all the possibles over here so we can test them. 4, 1, and 6, 2. So if we have this case where 2x minus 3y equals 6, we'd have to test all of these. So first, if x is 0 minus 3 times negative 2 equals 6, This is 0. Negative 3 times negative 2 is a 6. Oh, this one works right off the bat. 6 equals 6. Let's test another one just to see. 3, 0. 2 times 3, since the x is 3, minus 3 times 0 equals 6. 2 times 3 is 6. 3 times 0 is 0. Well, that also works. How about 4, 1? 2 times 4 minus 3 times 1 equals 6. This is 8 minus 3. Okay, that doesn't equal 6, which makes me think, did we do something wrong with one of these? Did I do something? Because we got 2 correct answers here, it looks like. How about 6 and 2? 2 times 6 minus 3 times 2 equals 6. 12 minus 6 equals 6. This one works too. So there's only one of these that doesn't work. This one does not work. Which makes me think, if we graph this line, all of these are points on the line. This one's not a point on the line. So let's graph it and look at that just to see if that's the case. Because that's what it's going to doing for us here. Let's see. If we graph 2x minus 3y equals 6, there's the line. And then I'm going to do all 4 of these points. 0, comma, negative 2. See, 3, comma, 0. 4, comma, 1. Oh, I didn't put the first. No, it automatically put the parentheses for me. And 6, comma, 2. Okay, let's label all these. Oh, look at there. Sure enough, negative 2, 0 is on that line. 3, 0 is on that line. 6, 2 is on that line, but 4, 1 is not. So that's why when we did the math with x equals 4 and y equals 1, it did not equal 6. Because if it did, it would be on that line. So when you graph x's and y's, if they're on the line, it should make the equation true. See, that was true. 6 equals 6. 6 equals 6. 6 equals 6. 5 equals 6. That was the 4, 1. So when you're graphing a line, what you're doing is you're graphing all the xy points that make the equation true. All right, so what did it ask us to do here? Which of the values below is the solution? Select the correct answer and hit submit. Well, there's several. Let's say that one. This pair is a solution. So it knew there was more than one solution then, right? Yeah, this is a solution. We could have selected any of those 3. But when you say this one, whoop. So they gave us 3 correct answers. That's how you want a test to be, right? Give me multiple choice and 3 of them could be right. As you can see, one variable equations only contain one solution, but 2 variable solutions can have many solutions. That's what they're showing us there. See, with 2 variables, there's lots of different solutions. But how many solutions will there be in a 2 variable equation? So on this one, an infinite number of solutions. All right. There are infinitely many points on this line because it goes on forever. So that means there's infinitely many solutions to 2x minus 3y equals 6. All right. You know that a linear equation with 2 variables has an infinite number of solutions. But what about a system of linear equations? It says you can solve this by graphing. So they want us to graph these 2 equations. So let's go do that. So our first equation is y equals 3x minus 7. I wonder if I can just copy and paste that in there. Oh, yes, that works real nice. And then we'll copy and paste this one. Okay, here's our 2 equations. By graphing, we can see that there's only one point that those 2 lines have in common. We can substitute 2 for x and negative 1 for y in either one of these equations, and it should be true. So if x equals 2, 3 times 2 is 6 minus 7. That equals negative 1. And the y is negative 1. So it'd be negative 1 equals negative 1. On the other one, y equals negative 2 times 2. That'd be negative 4 plus 3. That's also negative 1. So we see on this that there's one solution. Let's look at the next example there. Okay, for the first equation, start by plotting the y-intercept at -7 and the slope is 3. Okay, it's telling us how to do this. But like I say, we did it on Desmos, but we didn't have to worry. So it says 3 was the y-intercept, and you do a negative slope, right? Slope of 3. Oh, the y-intercept -7. They're doing the first one. They went down to the y-intercept at -7 and did a slope of 3 going up. But like I said, we can do all this by using Desmos and don't have to do it all by hand, unless you like to. All right. The solution, here's the important thing to know. The solution to a system's equation is the point or points on the graph where the two lines intersect. So is it possible for this system to have more than one solution? Could there be a second solution other than 2, -1? Any thoughts on that? Could there be another solution? Should I just zoom out? It's like, well, that's the only solution because you're zoomed in so far, Mr. Brock. If you zoomed out, then we can see the other solutions. These are both linear equations, right? These are straight lines. And if they're both straight lines, when are they going to be able to touch each other again other than this? Because if we go out, they're going to get farther and farther away from each other. Look, I'm zoomed out to over 1,000 now. They're just getting farther and farther away from each other in every direction here. So there's never going to be another solution. This is the only point right up here that these two lines are ever going to intersect. There's only one solution. Now, if these were like parabolas or something, we might have more solutions, right? Because it might curve around and hit it again. But this is not a parabola. This is not a circle. This isn't, this is a straight line. So with linear equations, there can only be one solution. Since the lines intersect at exactly one point, there can only be one solution. There's only one point that both lines share. And there's that point, 2, -1. They checked it there. Now, it is possible for two equations to be graphed on a coordinate plane and have no intersection. So if we look back at last week's lesson, we can see some of those, but let's put these two equations in here. And 9x plus 3y equals 3. See, these two lines are parallel to one another. There will never be a point where both of these touch each other. As I zoom out, we can see they go on and on forever, but they never get closer. They never touch because they have the exact same slope. And since they have the same slope, we know that there's no way they'll ever touch. And there's no solution. There is no point anywhere that is on both lines. So first they graph that one, then they graph that one, and they have the same graph that we just put on Desmos. And you can see that the lines do not intersect. They have the same slope. All right, and then infinite solutions. Oh, look there. If I turn off the one line, the red and the blue are the exact same line. So since the red and the blue are the exact same line, every single point that's on the red line is also on the blue line, and every single point is a solution. This is a solution. This is a solution. This is a solution. This is a solution. 1.12 and 3.24. All these infinite number of points that's on each line is a solution. There's an infinite number of solutions. So they graph it there, and they graph that one. It's the exact same line. So infinite solutions is the answer because we can't list them all. They go forever. All right. Let's look at page 3. Graphing is a lot simpler, right, guys? We don't have to do all that math. We just look at it on the graph. And as long as you know what you're looking at and know how to interpret what you're looking at, graphing is quicker. So, here they go. Finding solutions using technology. This is where they let you use graph software, a website. Let's look at a real world scenario. Peter wants to get the best deal on an internet provider. Mobile Llama charges $25 a month with no setup fee. You bet, Dane. Discount Internet charges $10 a month, but you got to pay $50 to set up. So you got to pay $50 to start your plan, and then you only pay $10 a month. Over here, you don't have to pay anything. Just start, and you pay $25 a month. Which plan is better for Peter? So graph the systems of equation to find out. So first, you kind of come up with two equations. So here's Mobile Llama. It's just basically y equals 25 times x, and x would be the number of months, right? So after 1 month, you've paid $25. After 2 months, you've paid $50, et cetera, et cetera. Discount Internet, there's this $50, but it's just once, just plus 50. And then 10x would be $10 for each month. So let's graph those. Y equals 25x. Woo, well, look how steep that is. It goes up real fast. And the other one, we only pay $10, but we start at $50. So we got to look up here where they cross each other. Let's see, what is the point where the solution is? Oh, looks like it's that point right there. 3.333 and 83.333 repeating. That is the point that both have in common. That means it depends on how long Peter's going to have his phone. If he only needs his phone for 3 months, I'm going to turn on this phone, I'm going to have it for 3 months, and then I'm going to stop it. I'm not going to pay after 3 months. Then this says, oh, wait a minute, was it plus 50? Yeah, that's right. 10x plus 50. So this says, then he's better off going with the green plan, the 25x. Because in 3 months, he'll just pay what, $75. If we go back to the point where the 3 is, let's see. Oh, I'm on the wrong line. Yeah, at 3 months, if we go to the 3 months, it costs $75 with the Mobile Llama plan. But if we go to the other plan at 3 months, where's the 3? Getting right there. You've got to pay $80 with the other plan, Discount Internet. $80. So it's cheaper. But if he keeps it longer than 3 months, now it reverses. Let's go to, what is this? Is this the 4? 5. Let's go to 5 months. You spend $100 with the Discount Internet here, where the other one at 5, he's spending $125. So that's just a way to graph both plans and figure out which plan would be better. So it just depends on the timeline. 3 months or less, he should be on the green plan, the $25 a month plan. More than 3 1/3 months, then he needs to be on the Discount Internet plan. So let's see. Graph them both. There's the graph point. There's that point 33383.33. The graph intersects at 10/3, which is 3.333 repeating. This is where understanding the scale and the units for graph are important. So after 10/3 months, or 3.33 months, the two companies will have the same cost at that point. After that, Discount Internet is cheaper. If the scale was off, these large numbers would not have been found, right? You got to be able to zoom out. Like we were just looking, down here where we usually look at graphs, we wouldn't be able to tell. You got to zoom out enough to where you can find that. So after that, Discount Internet's least expensive. You can check the reasonableness of your answer by thinking about the domain and range. Recall that the domain is all the input or x values. So the domain would really start at 0. We don't have negative months. So it'd be from 0 forward. So it's reasonable to assume all the values are positive or 0. But that's how you evaluate that. So look at this. Elaine buys 10 collectible baseball cards per month. So every month she's buying 10 baseball cards. Cy sells 5 cards from his collection of 90. So he's got 90, and every month he's selling 5 of them. He's bringing in some dollars. He needs something done. At what point will Elaine have more than Cy? She starts out with 0, but she's buying 10 every month. And he starts with that. So we can graph those two situations. If she's buying 10 every month, y equals 10x, but she starts at 0, right? So plus 0. She starts with nothing and buys 10 every month. So there's what it looks like after 1 month, 2 months, 3 months, 4 months, etc. He starts with 90, and you can do it as this way if you want, and he's selling 5 every month, 90 minus 5x, which is the same as y equals negative 5x plus 90. Those are the same graph. See the blue one and the red one, the exact same graph. So at what point will she have more? Well, at this point, they have the exact same. At 6 months, they will both have 60 cards because she's purchased 60 and he's sold enough to where he only has 60 left. So after 6 months, Elaine's going to have more cards. Before 6 months, Cy has more cards. Check your work. Here it is. Elaine's collection going up, his collection going down. At 6 months is when they have the same amount. Beyond that, she's got more. Before that, he's got more. So let's go to page 4. Multiple representations. Now this is a good one. I'm gonna write this down because you're gonna see this and then you're gonna like, I don't know how to do that. Okay, you're gonna see this and you're gonna try to graph it so you can have that quick, easy solution. And you're gonna be a little confused. Because like, okay, there's only one X in here. There's no Y, right? So there's no Y at all. So it's like, okay, we should be able to solve this. And which means we should be able to solve it by graphing as well. I mean, I know we can solve it on paper, right? We can move all the X's to one side and move the numbers to the other side. And we can solve this just like we solved this 2x minus 4 equals 10. We can get to X equals a number. But you're like, okay, but this is 2 equations. I should be able to graph that. So what happens if we try to graph it exactly like it looks? Let's see. Here it is. 5x minus 11 equals negative 2x plus 3. It's like, all right, I want to know the answer to this. I want to do it by graphing because that's quick. Oh, wait, I did. It didn't copy, did it? Copy. It's not the right equation. There it is. 5x minus 11 equals negative 2x plus 3. All I got is a straight up and down line. And you're like, what? I have a line at x equals 2 and y equals everything. Okay, I'm confused, Mr. Brock. I know that this is not a straight up and down line. This is not a straight up and down line. To graph this, yes, we can still solve by graphing. We can. But we have to break these into 2 equations. You got to do y equals the first one and y equals the second one. There they are as 2 separate equations. Now notice where they meet. They meet at x equals 2, which is where that up and down line was. This was x equals 2. That will give you the x answer. It just doesn't give you the y. The solution is the point 2, negative 1. That's the solution. But you can't see it when you graph it this way because all you get is that up and down, straight up and down purple line right there. And this drives me crazy. Let me do this. Step 1. All right. So if you have this type of equation, you have to break it into 2 different graphs. Graph the left side and then graph the right side, like I did right there. There's the left side, there's the right side, and there's the solution. Let's see what our lesson says about that. That does not look like a system, does it? Right? Not if you graph it like it is. The substitution method says that if you have a system like this, y equals 2x plus 2 and y equals x plus 4, you can substitute x plus 4 in for y, and it's going to look like that. So basically, when we see this, this is like solving this system of equations. Y equals 5x minus 11 and y equals negative 2x plus 3. This is the systems of equation that you're solving. But what's happened is we said, okay, well, if y equals this, then I can just take this and substitute it in for y right there. If I substitute that for y, because that's what y equals, then I get this. Look, I took that and I substituted it in for y. So that's why it looks like this instead of looking like this, because they've already taken the first step of substituting in for y. That's why the y went away. We only have x's. That makes sense? Well, we have no y now because we substituted it out. So this might be a good place to stop and go back and let's review last week. Because we didn't get to spend a lot of time last week on substitution. We spent more time on elimination. So I want to look at this together. If you have pencil and paper there, write this equation down and let's solve it by substitution and elimination. We're going to do both. Let me give you a moment to write that down. If you've got that written down, do whichever method you want first and see if you can come up with an answer. I'm going to work slowly because I want you to get an answer before I do. And what does it mean for this system equation solving either by substitution or elimination? Either way, what answer you can get. And then we'll check it by graphing because we can always graph it if we want to. But I'm going to solve it by substitution first, which means I need one of these to either be x equals or y equals. Doesn't matter, whichever one I want to do. I can do x equals or y equals. Which means if I want to do substitution, I should pick an equation that would be easy to do that. Look at this. I've got a 9, an 8, and a 13. I can do x equals or y equals, but it's going to be dealing with a fraction. Because these numbers do not work well together, right? 8, 13, 9. There's nothing in common there. They don't have any numbers in common. So when I try to get just x equals or y equals by dividing by 9 or dividing by 8, I'm going to have a fraction, which is fine. I can do that. But if I look at the other equation, I've got a 3 and a 6 and a 6. That makes me think I won't have a fraction because those all have a common denominator. 3 goes into all of those. So I'm going to choose the second equation for substitution, and I'm going to choose the x. So I don't care about the y. I'm going to do x equals. So I'm going to write 3x plus 6y equals 6. And I want to rewrite this to just be x equals. All right, so we're doing substitution. Substitution. I need to get everything that's not an x on the other side. This is not an x, that's a y. So I've got 3x left on this side. Over here, I've got a y and a constant. So I got negative 6y plus 6. I can't put those together because this one is not a y. It's just the number 6. Now divide by 3. X equals negative 6y divided by 3 is negative 2y. And 6 divided by 3 is 2. So y equals negative 2y plus 2. All right, if I'm ahead of you, I'm going to stop there for a moment. At this point, we have to use the other equation now. And we have to substitute what x equals in for x. That's what x equals. All right, I'm going to pause and let you do that on your paper. I'm going to come back and do it, but I want you to do it first. Take this equation, substitute it into that first equation, and then you should only have a y at that point. Solve for y. See, I'm pausing here. If you get to an answer, go ahead and put it in the chat. If you get that far ahead of us, that'd be great. I could have done y equals if I wanted. I would have had a fraction of 1/2, which isn't too bad to work with. But when I looked at that, it's like, oh, the x might be the easiest. All right, I'm going to do the next step. Hopefully, you're already ahead of me on the next step. 9 times x. 9 times, this is x. Okay, so that's 9x, right? Because this is x. In the second equation, this is what x is. Plus 8y equals 13. So this is the first equation rewritten. So all I did is I just wrote the first equation again, substituting x for what x equals. If x equaled 4, we just put a 4 in, 9 times 4. But x doesn't equal 4. It equals negative 2y plus 2. So we have to put negative 2y plus 2. It's just like putting 4 if it was equal to 4. Whatever it's equal to, it's fine. Okay, and now get rid of your parentheses. Like I say, maybe ahead of me. That'd be great. We have to distribute. So the 9 has to be multiplied by everything inside the parentheses. 9 times negative 2y. 9 times 2. And then the rest of it, we just copy the rest down. We didn't do anything with the rest of it. All we did was get rid of the parentheses. That's it. Now we have like terms on the same side of the equal sign. See, there's the equal sign. So since these are on the same side of the equal sign, we can just combine them. Negative 18y plus 8y is negative 10y. And then this is still there, so we need to copy that down. And then we're still equal to 13. All right, it's all working. Well, it's getting easier and easier to solve now. We're trying to solve for y, which means we don't want this 18 on this side. So negative 10y equals 13 minus 18. Divide by negative 10. Y equals negative 5 over negative 10 is a positive. Y equals 1/2. Y equals 1/2. That's half of our solution, right? Because we need an x and a y. We need to know what x equals. Y equals 1/2. But what is x? We can choose either equation, whichever one we want. We just need to substitute. I'll go ahead and do the second one. 3x plus 6 times 1/2 equals 6. That's fine with it being worth a half because it's easy to multiply 6 times a half. Or if we use the first equation, we'd be multiplying 8 times a half. That works real nicely. What is 6 times 1/2? Right? Now we just want to solve this for x. Divide by 3. So our solution is x equals 1, y equals 1/2. That's the answer. I'm going to leave that if you're copying down those notes. We're also going to work this by elimination. We're going to take the exact same problem, because we can do it by any of these three methods. Just with some equations, one method may be easier than another method. Elimination. All right, I'm going to move down here. I'm going to leave so that we can see it if you need to. I want to do this by elimination. This is where I add these together and either the x or the y goes away, which right now that won't happen, right? 9 plus 3 would be 12, 8 plus 6 would be 14. Neither one of them go away. So I need to change one of these equations. So if I take the second equation and multiply it by a number, the 8 and the 6, that's not going to work. I'd have to multiply it by like a 1.3333, or I got to multiply both equations. I could do that. But look here, this one looks really easy because a 9 and a 3, if I multiply by a -3, then this is -3 times 3 is -9x. Oh, look, that's what I'm looking for. I'm looking for something to go away. 9x and -9x. So let me finish multiplying this. -3 times 6y. And then don't forget to do the other side as well. I have to do both sides or I've changed the equation. So I can rewrite these over here. 9x plus 8y equals 13. And then my new equation, which is the same equation, just in a different form. So now I've got 9x plus 9y equals 13, which is exactly what the top one was. The second one, I multiplied both sides by -3. So it became -9x minus 18y equals -18. Now I can just add these together. 9x plus a -9x. There's no x's left. X has gone away. 8y minus 18y. Add those together. I got a -10y. 13 plus a -18. Oh, look, I'm same place I was at right here. I got -10y equals -5. Divide by -10. Y equals 1/2. I got the same answer that I got over here, which is good because I should. And then to get to x, I go back and do this exact same thing. I just take the 1/2 and I put it back into either equation. Let's put it in the other equation this time, just to prove it to ourselves, because we did it with the second equation up here. So if I do 9x plus 8 times 1/2 equals 13. So 9x plus 8 times 1/2. That means 1/2 times 8. 1/2 of 8 is 4. Subtract the 4 from both sides. So I've got 9x equals 13 minus 4. Same answer. Exact same equations. Exact same equations right here. Up here, we did it by substitution. Down here, we did it by elimination. And either way, we come up with 1 for x and 1/2 for y. So let's look at the third way again. We said that we can solve these by graphing because that's what this week is talking about, graphing. So let's go over here and put both of those equations in here, the exact same equations that we just solved. 9x plus 8y equals 13. That was the first equation. And the second equation was 3x plus 6y equals 6. And what is the solution? Oh, I don't like all those. I want step 1. I don't want the minor grid lines. Thank you. There we go. The solution is 1 and y equals 1/2. X equals 1, y equals 1/2. The point 1, 1/2, which Desmos does as a decimal, 0.5 is 1/2. So that just kind of shows us We can get the same answer by substitution, 1/1/2, elimination, 1/1/2, or by graphing, 1/1/2. We did one each way. Let's see, they have a different equation. Oh, they're doing the 5x minus 11, 2x minus 3, either side. Like I say, if you graph them individually, you get the 2, -1. We looked at that earlier. Tables and graphs. Okay, find the solution to the system equation using graphing. So this equation, they don't give us the equation for that, but we could figure it out because it's got a y-intercept of 3. So let's do this start out. It's got a y-intercept of 3, so y equals 3. And the slope is what? It goes down 3, 1, 2, 3, and over 1. So it's a -3 slope. So -3x. There's the same graph. See, it goes through these 2 points. See, it went through 0, 3, and 1, 0. That's the exact same graph. And it has this table over here, the point -3, -4. So let's put that point on here. -3, -4. There's one of the points. -2, -3. And the point -1, -2. All right, let's label those so we can see where they're at. Okay, so it's wanting to know what's the solution to this systems of equation. If this table has points that are going up 1 every time, and this graph is a negative slope going down, where are these going to intersect? Easier to see by graphing than try and do it algebraically, right? So that means this point, then this point, then this point. The next point would be right there at 0, -1. And then the next point's going to be right there, 1, 0. That's the solution. That's where they're going to intersect. That's where the points on this table are going to intersect with this line here. Figure that by graphing. So this says step 1, put the points right there. Connect them with a line. You can do that. Step 3, where do they intersect? At 1, 0. Right, yeah, we can look at this and say this is actually y equals x plus 1. It's minus 1. It went to, yeah, and we can see they intersect there at 1, 0. Here's another one. Put the points. You put the points there, turns out it's parallel. That would have no solution. All right, here's our lesson summary. Solving systems equations graphically. So a system equation is defined as 2 or more equations use the same variables. The solution to these equations, if it exists, is the point or points of intersection between the 2 lines. So you put the equations in slope-intercept form if necessary. You graph both of them on the same graph and identify the point of intersection. And remember, for example, if you have 4x plus 2 equals 5x minus 1, you can rewrite that as y equals 4x plus 2 as one graph and y equals 5x minus 1 as the other. You put both of those lines on the same graph. And then the solutions to the system equations are the solutions to this original equation. At that point, it was x equals 2. Equations can be represented verbally, like a word problem, algebraically, could be in a graph, it could be on a table. And remember, systems of linear equations, here's the important thing. They only have one solution if they intersect, no solutions if they're parallel lines, or infinite solutions if they're the same line. And that's the 3 possible answers you can have. One solution, which you can tell me, xy, what is the xy? No solutions are infinite solutions. So let's look at the practice they give us. They give us 1 page of practice problems. All right, solve each system of equations by graphing. and then you can check your work. So here are activity 1 has 1, 2, 3, 4, 5, 6 problems. See, there's 6 problems right here that we can check. Activity 2 is a word problem, and it's got two different word problems. Activity 3, sketch a graph that helps, but put together an idea before checking your solutions. Two linear functions intersect at this point. If f of x has a positive slope that's larger than g of x, which function has a larger y-intercept? Oh, that's a really good one. All right, let's go back here first, and we're going to come back and try that, though. Let's go back to activity 1. So we'll do, let's see, let's not do the first one. We'll do like the 4th one here. Let's skip over that one. Oh, I went too far. That was the 4th. Graph this on your own paper. Well, we're going to graph it on Desmos. So what is the solution to this? Let's see. Let's go to Desmos. Get rid of all these ones we were playing with here. 2x minus y equals 5. And then our other equation, 4x plus 4y equals 8. That's right. Okay, so when we graph these two equations, we find the point of intersection is not a nice, easy integer, but still that's where they cross. They cross at 3.11111 and then 1.222. So this one, we're kind of happy we did not do this by substitution or by elimination, because we'd be dealing with some really nasty fractions, right? We'd have some fraction answers for sure. Let's check that against what they come up with. This is how we do this. We check, we get an answer, and then we go back and say, okay, check my work. Look, they got 3.11, 1.22. That's the same thing we got. It just repeats. That is the answer. So see more. There's the graph, 3.11 and 1.22. All right, so there's good practice right there. So there are 6 of these. So try all 6 of those. We just did that one, but you can go back to the first one. Oh, there's a good one. The second one has a fraction, 3/2 x minus 1. But you can still, I don't know if it'll copy into Desmos, but you could type that into Desmos. Let's see if we try. No, it doesn't like the 3/2. So you have to type that one in. But remember, if you're doing a fraction, you just do divided by, and then have to move over to make sure. If you don't move over and you leave it there, it's going to have it underneath. You don't want the x as part of your fraction. You got to go over here and make the x next to your fraction. See, so that'll give you a little trouble if you're not careful. All right, let's go look at activity 2. We've got 2 different ones here. All right. So let's look at the second one. You are preparing for a final exam that has 50 questions. Some of the questions are worth 5 points and others are worth 3 points. There's a total of 180 points. So you're trying to figure out how many 5-point questions are there and how many 3-point questions are there. So let's call the 5-point questions. This is a good one. Let's write this down, figuring this out. First thing we have to do to be able to solve this is we need some equations. So anytime we have a word problem, we got to figure out what's the equation. So there's 2 types of questions. There's type 1, which is worth 5 points, and there's type 2 that's worth 3 points. So let's just call these X and these Y, right? So X will be 5-point questions and Y will be 3-point questions. And we know there's 50 questions. So we know if we add the 5-point and 3-point, oh, not the 3, X plus Y. We know that X plus Y is 50 because there's 5-point and 3-point, but there's no more than 50 questions. There's 50 altogether. So there's one of our equations. And we know that the X is all worth 5 points. So those are 5 points each. And these are 3 points each. And we know the total is 180 points. That gives us 2 equations. Assign a variable. Figure out what variable you want to use. And we know that, okay, this type of question, we're just going to call X. It's worth 5 points, which means each one question is worth 5 points. So 5 times each question plus 3 times each question here will give us a total of 180 points. 5x plus 3y, 108. That'll give us our total points. We just need to know how many 5-point questions there are and how many 3-point questions there are. And together, we know the 5-point plus 3-point questions are all 50 total. So let's solve this. So I'm going to solve it first by substitution because we didn't get enough practice doing that. And this one's a real easy one for substitution because we've got an x and a y equals. So let's just pick one. Let's just say, all right, I'm going to make it x plus y equals 50. Subtract the y. X equals negative y plus 50. That was real easy to get an x equals that I can substitute into the other one. 5 times negative y plus 50 plus 3y equals 180. Substitution, right? This is what x equals, so I substitute it in for x. Oh, and in this x. I have to use the other equation. Since I did this equation, I have to use the other equation when I substitute. I substitute it back into this equation. Get rid of the parentheses. Negative 5y plus 250 plus 3y equals 180. These are on the same side of the equal sign. So negative 5y plus 3y is negative 2y plus 250. I'm just solving for y now. So negative 2y equals 180 minus 250. You need your calculator. You can do that, but 180 minus 250 is negative 70. Y equals negative 70 divided by negative 2. Negative divided by negative cancels each other out. There are 35 questions that are worth 3 points each. We can substitute back into here. X plus 35 equals 50. So we know X equals, there's 15. So there's 15 questions that are worth 5 points each. There's 35 questions worth 3 points each. Well, let's take these two equations that we created from that word problem and let's graph them just to double check our work, especially since this is a graphing lesson this week. We said the X questions plus the Y questions will be a total of 50 questions. And each of the X questions are worth 5. Each of the Y questions are worth 3. And there is a total of 180 points. Now notice it's off our graph because we're zoomed in too far. We just need to zoom out. Oh, there they are. Let's find this point that they have in common. What is that point right there? 15 and 35. X is 15, Y is 35. And when we solved it, we said X was 15, 5-point questions. Y is 35, 3-point questions. Same answer, 15, 35. X is 15, Y is 35. We did it by substitution on paper. We did it by graphing on Desmos and should get the same answer either way you do. I want to look at this one real quick. And oh, there's 3 of these, huh? Oh, nice. Okay, let's look at the first one. 2 linear functions, f of x and g of x, intersect at the point 2, 3. All right, I'm probably going to do some different sheet of paper because I'm out of room. And we need to have a picture of it in our head, what's going on. They intercept at 1, 2, 1, 2, 3. says if f of x has a positive slope that is greater than g of x, which one has a larger y-intercept? Okay, all we know is that we have two lines. Let's see, how can I represent those well without drawing on there? Let's have to use pencils. All right, so we have these two lines that intersect here, right? They intersect at that point. Let's say f of x would be a different color. So let's say f of x is blue. F of x is blue and g of x is orange or yellow, whatever color you want to say this is. And they both intersect right there. And it says if f of x has a positive slope that's larger than g of x, larger than g of x, which has a larger y-intercept. Okay, so a positive slope. We know that means it's going up, right? It's going up. This is a negative slope. That's a positive slope. So it's going up. And the more it goes up, the bigger the slope, right? This would be like a slope of 1/2, a slope of 1, a slope of 2, a slope of 3, a slope of 4. So it has a slope, a positive slope that's larger than what g of x's slope is. Let's say g of x has a positive slope. It could have a negative. It doesn't matter for this problem. But all we know is f of x has a larger slope. So if they both go through the same point, and this is, let's say this has like a slope of 1 or 1/2 or 0.1, something smaller than what f of x has, it asks which one has a higher y-intercept. Even if g of x has a negative slope and they go through there, it's going to work the same way. All I know is that g of x is not like this. It does not have a bigger positive slope than f of x because it said fx has the larger positive slope. So at best, it could be close, but not quite the same, somewhere here. So put that in the chat. Which one's going to have the larger y-intercept? That's what this is asking. Which function has a larger y-intercept? If f of x is the blue one, and it has a y-intercept that's bigger than g of x is going to be something smaller, right? We'll say it's just a little smaller, like that. Which one has the bigger y-intercept, f or g? This is f, this is g. This is where we're going to be able to think through these things. Picture what in the world are they talking about? What in the world are they talking about? Put that in the chat. F or G? Who has the larger y-intercept? It's a little bit of a Algebra 1 review when we talk about y-intercepts. Right, that's going back a little bit in their math. But by this point, we should know what a y-intercept is. We'll talk about it in just a moment here. Wait to see what you come up with an answer. This is a great test question. I don't see anything in the chat. Everybody fall asleep? Are you confused? Do you not know? Put a question mark if you don't know how to figure this out. Corey's not sure. Let's put it in Desmos as well. It's going to go through the point 2, 3. All right, let's put 2, 3 on there. Gonna zoom way back. Get way back down here. Okay. Here's the point that's both of them are going to go through. So f of x, I can type it in that way, is going to have a positive slope. Let's say 2x minus 1. Okay, that goes through that point, right? And there it is. So let's say g of x only has a slope of 1x, and goes through that same point. So they both go through 2, 3. F of x has got a larger slope, positive slope. What is f of x's y-intercept? Well, it's right here for this one. It's at 0, -1. So if g of x has got a smaller slope, its y-intercept has to be higher. Doesn't matter if I pivot this to where it's a negative slope. Now it's going to move way up here. Let's say that's a negative slope. In order for it to go through that point, oh, got to go higher than that. So even if it's a negative slope going to that same point, now it's up here to 5. It's a lot bigger y-intercept than the f of x. But however it is, even if it's, let's see, that's a 2. What if this is a 1.95 slope? And I've got to go minus 0.95 or something. Does it go to the same point? Did I miss it? I think I missed it. That's real close. Well, now they go to the same point. They go to the same point right there. 2, 3. But look, g of x still has a higher y-intercept. So for this question, g of x has to have a higher y-intercept because its slope is smaller. G of x has a larger intercept. Why? Well, the two functions make it to the same point. That means since f of x has the larger slope, from the y-axis to that point is going to be greater, so it's got to start lower to get to that same point. Since it's steeper, I like how that thinks about it. Since going to the same point, if it has a bigger slope, it's steeper. That means the y-intercept's got to be lower for it to hit that same point. Because another one coming here is going to have a higher, it's not as steep. So the y-intercept's got to be lower if it's steeper. And sometimes it kind of helps to draw that out. Like I was doing on paper, draw it out and say, if this is here and this is here, yeah, this one's higher. Even if you don't know exactly what g of x is, even if we don't know exactly what it is, we know that it's got to be higher. G of x got to be higher. It's one of those you just got to think through it. It's either f of x or g of x has the higher y-intercept. But the higher it is, the lower the slope has to be to go through the same point. All right, let's go look at our assignment for the week. That's the end of the lesson. Read the examples and lesson, work the practice problems. Make sure you can answer those 2 questions at the beginning, and then let's do the assignment that goes with it. Solving systems of equation graphically. Start, you get 3 attempts. Solve this system. 2x plus 2y equals -6, 3x minus 2y equals 11. By using graph paper or graphing technology, put it on Desmos. What's the solution? So graph both of those. Where do they cross? Here's another one. Graph. This one, I like this. Gives you the equation and says, which one of these is the graph? Well, you can still go to Desmos and graph these and see which one of these graphs it makes. They're very different. Now, here's a word problem where you got a table. So at the end of April, Mandy told Bill she's read 16 books and reads 2 every month. Okay, so hers, you got to write an equation for. Bill tracks his reading on a table. So he starts with 4 books in May and reads 4 books every month. Using this table below, what month will he have read the same amount of books as Mandy? All right, figure that out. However you need to do it, graphing it or making the table bigger. Keep making the table bigger and then track Mandy's. What would make a table for Mandy if you want to? And here's a graph. Which one of these is this the graph for? And remember, this is one of those that you got 7x plus 3 equals x plus 3 or minus 3. You have to graph this separately than you graph that. One of these lines is the graph of the first equation, and the other one is the graph of the second equation. Oh, I didn't mean to select that. I don't know if that's right or not. So, all right. It's one of these. But that's it. Five problems, guys. 5 problems. All right. If your grade is below 70%, then I'll see you. Oh, this week I need to look. I didn't look. I think it is an actual A week again. because we didn't have class yesterday. But let me look at the calendar real quick and see. High school hub, AB calendar. To see, this is the first week of September. It is an A day. We have an A day again this week. So we have class Thursday if you need help, or if your grade's below 70. You can come to class even if your grade's 100%. If you're stuck and having trouble in this assignment, come to class. Say, Mr. Brock, I'm lost on number 3. I don't know how to get there. Number 5's got me totally blown out of the water. Help me. So we'd love to do that. Give you all the help you can. So, all right, guys. Some of you may see Thursday, and I'll see next week. So have a great week.
What? Just ride. I just need a ride. Yeah. I just wanted a little ride. That's all I needed. Come on, Big D. Come on. What is it? What?
Painting.
I just wanted to go to the wedding. That's all I wanted to do.